You have an idea for a web app. You open a chat window, describe the concept to an AI, and it generates a working draft. You notice a missing feature, so you type a quick follow-up request. The AI obliges. But as it adds the new feature, the specific database architecture you established in the first prompt vanishes. You correct the mistake. The database logic comes back, but now the front-end routing is completely scrambled. This iteration cycle is called vibe coding. You start with a vague concept, describe it loosely, and attempt to refine the codebase through a continuous, scrolling conversation. It is the most intuitive way humans engage with generative AI. For a quick, self-contained weekend script, this conversational approach works remarkably well, but apply it to a sprawling, multi-file codebase, and the process eventually collapses. This structural collapse stems from a procedural error, trying to build complex systems through casual conversation. Asking a chatbot to hold thousands of lines of interconnected logic in a single thread is like directing a construction crew through a series of unrelated text messages. With every new prompt you type, a hidden structural degradation occurs beneath the surface of the chat window. The first point of failure is context loss. This chart represents the AI's working memory. As each new instruction drops into the stack, it receives priority weight. The constraints you established 30 minutes ago are pushed so far down that they effectively fade out and become invisible to the model. Then comes assumption drift. When you ask for an authentication system without specifying exactly how to handle tokens, the AI fills the blank spaces with its own defaults. Those guesses are usually logical, but they rarely align perfectly with your specific project constraints. Finally, you hit pattern violations. Without explicit rules, the AI mimics broad internet best practices. It might write functional code, but it does so while violating your repository's established formatting, type safety, or architectural standards. These three mechanisms amplify each other. The context loss prevents the AI from remembering your corrections. Assumption drift introduces new logic you didn't ask for, and pattern violations clutter the codebase. By prompt 15, you are managing an escalating crisis. The deeper you get into the session, the wider the variance becomes. Correcting this accumulated damage eventually takes more time than writing the code yourself. A single rolling conversation simply lacks the working memory to balance complex rules. The AI needs the entire architectural context, complete with strict boundaries, permanently locked in before the coding begins. This is where Spec-Driven Development, or SDD, steps in. It is a systematic four-phase workflow designed to provide the AI with the complete picture up front. Phase 1 is parallel research. Instead of a single thread, you direct the AI to spawn multiple independent subagents. They investigate different angles of your problem simultaneously. Because they operate in isolation, they return findings without carrying over bad assumptions from other parts of the project. Phase 2 is specification. You consolidate these findings into a permanent written document. This file acts as the explicit blueprint, detailing exactly how the system should behave and establishing measurable criteria for success. The most important elements in this document are the negative constraints. Telling the AI exactly what external libraries to avoid and which directories to leave alone is what keeps the project from sprawling. By separating the planning phase from the coding phase, the AI stops guessing your intent. It becomes a strict executor following defined boundaries, closing the gaps where assumption drift normally takes hold. Phase 3 introduces the refinement interview. Before generating any code, you instruct the AI to read your new specification and actively interview you about it. The AI hunts for hidden ambiguities. It might ask how a specific data conflict should be resolved, or what happens when an API limit is reached. Answering these crucial questions right now prevents you from making incredibly expensive structural pivots midway through the actual build. Only then do you reach Phase 4, task-based implementation. The finalized specification is extracted into a rigid checklist of atomic, sequential tasks. Here, context isolation is critical. The main AI orchestrates the checklist, but it delegates each task to a fresh, memory-whites subagent. If a subagent makes an error on task 7, it is contained. It cannot pollute the logic of task 8. Each isolated agent completes its work and commits the code independently. The entire process functions as a clean, controlled assembly line, allowing you to easily roll back a single failed step rather than untangling a massive broken chat log. Consider the math. You can spend 5 minutes prompting and 2 hours debugging a disjointed mess. Or you can spend 45 minutes researching and specifying your architecture, then watch the code align with your requirements on the first pass. This requires a shift in how you view your role. You are stepping away from the keyboard as a solo programmer. You are now a systems orchestrator, managing a highly coordinated, parallel development team. The code it produces is a byproduct. The true asset you are building is the specification document itself. That text file is a durable artifact that survives the session, preserving your exact architectural decisions for the next time you open your terminal. Building reliable, large-scale software with AI means closing the endless chat loops. It requires strict planning, establishing clear boundaries, and written documentation. It is time to move past the chat box and master the specification.